Okay, so what we've got here is a demo kit. It's actually our first iteration of the demo kit for our digital temperature sensor products. This kit consists of what we call our micro base board here that simply acts as the interface between the computer and the daughter card, which contains the digital temperature sensor. So it provides the I2C interface and protocol and information to the temperature sensor device. It utilizes an Atmel AVR microcontroller to do all that communication. On the actual digital temperature sensor board itself, we have simply just a power mux that allows us to control between 3 volts and 5 volts power supply for the devices. And this is actually the temperature sensor. So that is our AT30TSE002B digital temperature sensor that has the integrated 2KE². You can see in this particular example here, it's packaged in a 2x3 DFN package, which is actually extremely small considering what's inside silicon content-wise. And this is ideal actually for very portable applications. It's ideal for something like a lithium polymer battery, where obviously they have to be very thin. Also on this board we have some status LEDs that tells us when the temperature is in a normal condition or when it exceeds the low alarm limit or high alarm or critical alarm. And then this red LED is used to indicate certain temperature events and what's happening with the device itself. So this LED here is driven by the temperature sensor itself. It's a direct connection to the device's event pin, and that event pin is used to signify when a temperature threshold has been crossed in either the positive or negative direction, going up or down. And then these LEDs here are actually being driven by the microcontroller itself on the communication board. So we have our GUI interface here that we've developed, and what this interface allows us to do is allows us to set the temperature limits of the device. It shows the alarm status, it shows the current temperature reading of the device, and you can see here it's currently 29 degrees Celsius. And then it's got a temperature history plot that shows not only the alarm limits, the critical alarm limit, which is the red line, the high alarm limit, which is the orange line, and the low alarm limit, which is the yellow line. Might be hard to see. And then the current temperature is the thick white line. So I'd like to actually go ahead and show you this device in action. So I'll go ahead and I've already preset the temperature limits. I've got the low alarm limit set at 32 degrees C, the high alarm at 36 degrees C, and the critical alarm at 45 degrees C. And again, it's currently about 29 degrees C inside this building here. So I'm going to use a flashlight where I've removed the lens cover to go ahead and generate a heat source to heat up the temperature sensor device. And so I'm going to go ahead and place this on really close to the device, and you can see the white line there on the graph begin to increase in amplitude and rise as the temperature increases. And you can see the high alarm limit's already been exceeded. And if I take this heat source away, well actually I'll go ahead and leave it on here and see if we can get the critical alarm limit to trip. And that critical alarm limit could be set to indicate the device has gotten extremely hot and you need to shut down the system altogether versus just turning on a cooling fan. And there we go.
Bingo.
So now it's tripped the critical alarm as well. And if I take away the heat source, you can see the temperature drops pretty quickly. And the critical alarm has turned off, and the high alarm will also turn off once it drops below that orange line. So one thing about the digital temperature sensors is you can see on this board, for example, that there's no other components necessary needed to interface to it. Whereas a solution like a thermistor or a thermocouple is actually going to need a separate analog to digital converter and microcontroller to actually go through and convert the analog signal to a digital format and then process that information to figure out what the temperature really is. That's going to place additional strain on the microcontroller because it has to go off and service that function rather than using operating cycles to address a higher level function in the system. With a digital temperature sensor like this, you don't have to worry about that. It converts all the digital information itself, does the temperature measurement, and then just you can read the temperature from the device through the I2C interface. So now what I'd like to show you is actually more of a real-world application. I've got a fan over here, something that would be used like in a PC application, and a simple fan controller board. So another nice thing about a digital temperature sensor is it can directly control another circuit like a fan controller without having to need a microcontroller to do that function. Again, with a thermistor or thermocouple, you'd actually have to go through and have that microcontroller tell the fan controller what to do. So I'm going to go ahead and use the flashlight again to go ahead and heat up this, this board. There you go. So the fan is now blowing. So this is what would happen in a PC, for example. So if the PC temperature or the processor temperature started to get too hot, the fan would turn on to cool the processor, and then of course we take the heat source away, and once that temperature drops below the low alarm limit, the fan should turn off. And there we go. Another nice advantage of a digital temperature sensor like the 30TSE002B is that it does not require calibration. With a thermistor or thermocouple type of solution, every thermistor or thermocouple would require calibration in the system to know what the temperature is beforehand. So this saves additional cost and components for the system designer.